Hey there. Ever wonder how your phone recognizes your face, or how a robot learns to walk? It all starts with some pretty mind-blowing math, specifically, something called Neural Tangent Kernels and Fisher Information Matrices. Today, we're breaking down how these tools help us understand how neural networks really learn. Let's dive in. Imagine a neural network as a massive machine with millions of tiny knobs. When it learns, these knobs turn just a little, and the network's predictions change. The Neural Tangent Kernel, NTK, is like a map that shows exactly how those tiny turns affect the final result. It's the mathematical fingerprint of how the network adapts, like a compass guiding its learning journey. But here's the twist. When these networks have huge numbers of hidden units, think millions, the NTK starts to reveal a hidden pattern. It's not random, it's structured, like a symphony with distinct instruments playing in harmony. Researchers found that this pattern can be broken down into simpler parts called eigenfunctions. Think of them as the building blocks of the network's learning. Now let's talk about Fisher Information Matrices. This one's like a roadmap of how sensitive the network is to changes in its knobs. It tells us which knobs matter most. And here's the kicker. The NTK and Fisher matrix aren't just similar, they're deeply connected. Both have the same kind of spectral structure, meaning their eigenvalues, which measure importance, and eigenfunctions, the patterns they represent, line up in surprising ways. So what's in this spectral structure? For example, one key eigenfunction is the absolute value of the input, x. Others are combinations of features, like x1 or x2, or even ratios like x22, x2/x. These aren't random. They're the mathematical tools the network uses to approximate complex functions. It's like the network has a toolbox of patterns it relies on, and these eigenfunctions are the most useful tools in that box. And here's the practical magic. The researchers derived explicit formulas for these eigenfunctions. This means we can approximate what the network is doing. For instance, we can say, this network is mostly focused on the absolute value of inputs, with some tweaks for specific features. This isn't just theory. It's a blueprint for designing better AI, debugging models, or even understanding why a network might fail. So why does this matter? By uncovering these hidden structures, we're not just solving a math puzzle, we're unlocking the secrets of how AI learns. It's like finding the recipe for a perfect cake, step by step. And as networks get more complex, this kind of math will be essential for building smarter, more efficient systems. Thanks for watching, and stay curious, because